right, so this is a similar looking example to the last one we did. We've got a piecewise function, and we're going to use the definition of the derivative to show something about this. But there's one important difference here. The last one we looked at, we were showing that the function was not differentiable at x equals 0, and this one, it asks us to show that the function is differentiable at x equals 0. So we're going to expect some different things to fall out than last time. Last time we got that the limit did not exist, and if they're telling us to show that this function is differentiable, then I expect that limit to actually exist. All right, so let's go ahead and start by using the definition. Limit as h approaches 0 of f of 0 plus h minus f of 0. We're doing this at x equals 0, so I've put that in for x in my definition. And that is going to become, okay, so on this one, because I have a piecewise defined function, I need to make sure I'm using the right pieces for each piece of the definition here. So on this first expression here, I'm putting in values that are close to 0 but not equal to 0 for h. So here the input is not 0. So I'm going to put that into the first piece of the piecewise defined function. And instead of writing 0 plus h, I think I'll just simplify that to be h when I put that into my function here. All right, so we'll have h cubed times sine of 1 over h. All right, and then for the second piece of the numerator here, I'm evaluating f of 0. And so for that one, I'm going to be using the second piece of the piecewise defined function. When x is 0, the output is 0. All right, and then I want to simplify this expression and figure out what this limit is. So this minus 0 here on the numerator doesn't change anything, so I can drop that. And then I might notice that I have some h's that I can cancel from the numerator and denominator. And so I can make that h squared on the numerator. So let me just rewrite that. Okay, so now I need to think a little bit about how I'm going to tackle this limit. I cannot use a substitution shortcut because obviously I can't put in h equals 0. That would give me an undefined expression on the denominator. But this should actually look like a familiar problem. We did problems like this. This was actually one of the problems on your checkup assignment to do a problem similar to this from earlier in the semester. That this is a limit we can tackle using actually sandwich theorem. So we'll use this as a good opportunity to review what sandwich theorem says and how we might write that up. All right, so for sandwich theorem, we need to show that we've got this function sandwiched in between two functions that it's easier to evaluate the limit of. And the key to making that work is finding what those two functions are that you're going to use to sandwich this function here. And so one helpful thing to notice is to remember that the outputs of the sine function are always between -1 and 1, no matter what input you have. Right? So this is true for all values of theta. When I have h 1 over h in here, that will be true provided h is not 0. Right, I can't put in h equals 0 here, but remember that this limit is asking us about what happens when h is close to 0, but not at h equals 0. So I have this expression here bounding the sine of 1 over h function. And then if I multiply this expression through by something that is not negative, I will preserve the inequalities here. So if I multiply through by h squared, which is never negative, I get negative h squared is less than or equal to h squared times sine of 1 over h, which is less than or equal to h squared. So I just took the previous inequality and multiplied through by h squared. My goal was to get the function that we're working on sandwiched in between two functions that are easier to evaluate the limit of. So now I need to show that the limit of each of these squeezes to the same place. Remember that theorem is sometimes called squeeze theorem because you not only have to get the sandwich part, but those limits have to agree, so they have to squeeze to the same limit. So the limit as h approaches 0 of negative h squared is 0, and the limit as h approaches 0 of h squared is also 0. So that's the squeeze part of that theorem. Those limits go to the same value. So that tells us that the limit of this function in the middle, which is the limit we were actually after, is also 0. sandwich theorem. And here's our work for sandwich theorem over here. Okay, so we've shown that that limit does exist. So this is an important example of a piecewise function where we can use this limit definition of the derivative to show that a limit actually does exist for this derivative definition. So that tells us that that function is differentiable at x equals 0 and that the derivative at x equals 0 is 0. So this is the derivative at x equals 0.